Welcome back to video number 2 on Monday. May the 4th be with you. If you have not already seen the first video on our introductions, stop right now and watch that video because we went over something very important that you're going to want to have in front of you while we go through these properties. I'm going to take these off because I can't see. All right, this video, we're going to talk about the properties of exponents. There are 3 properties that we're going to focus on: product of powers, quotient of powers, power of powers. And I don't expect you to know those right now. We're going to go through each one and we're going to talk about how we use them the long way, meaning kind of what we did in the first video. And then we're going to look at some shortcuts based on patterns that we noticed. So for this video, you're going to need a piece of blank paper and something to write with, and just follow along kind of as we go. So property number 1, product of powers. So at the top of your paper or at a section of your paper, go ahead and write this out: product of powers. Let's think about just for a second what that actually means. What is a product? Well, we see that over here. Products mean multiplication. That means I'm multiplying powers. So in other words, these are multiplication problems where the factors in each multiplication or in each product are powers. It just means multiplying powers. So what happens when you multiply powers? That's all that this means. So we're going to look at some examples here, and you're just going to follow along on your paper. And then if you have this out from the intro video, that will also help us because I'm going to be referencing that quite a bit. So our first one, what does it mean to have a product of powers? Well, let's take, for example, if we have 2 to the 3rd power times 2 to the 4th power. What does that equal? Now, for this one, because we're going to start with bases that are actual whole numbers, and then we'll work into variables. But if you have a calculator in front of you, this will actually make a little bit more sense, or it'll help kind of explain what we're looking at. So on your paper, go ahead and write down 2 to the 3rd power times 2 to the 4th power. And we're going to find out what this is equivalent to. Well, to do that, we're first going to expand what we know 2 to the 3rd power and 2 to the 4th power actually mean. And then we're going to write it as an equivalent power, and then we're going to check using just calculators and multiplication. So what does 2 to the 3rd power actually mean? Well, 2 to the 3rd power means 2 times 2 times 2, right? That just means I'm multiplying 2 by itself 3 times. That's what powers actually mean. And what does 2 to the 4th power actually mean? Well, 2 to the 4th power means 2 times 2 times 2 times 2. So now we have 2 products that each of our powers represent. And what are we doing with those? Well, we're just multiplying them by each other, right? We have 3 2's over here times 4 2's over there. Well, what I hope you notice, and I'm going to bring this a little bit closer so you can see, what I hope you notice here is that all we have are just, it's just continuing the multiplication. We have 2 times 2 times 2 times 2 times 2 times 2 times 2. So in other words, how many total times are we multiplying 2 by itself? 1, 2, 3, 4, 5, 6, 7. So this is equivalent to 2 to the 7th. Why? Because you multiply 2 by itself 3 times, and then you're basically, you know, continuing that 4 more times for a grand total of 7 times. Now, if you don't believe me, go ahead, grab your calculator, and let's see what that actually means. So in your calculator, if you're using your phone, you're going to flip it sideways, and that will allow you to do our powers. So I'm going to go ahead and do 2 to the power of 3, which is 8, times 2 to the power of 4. And I got 128 as my answer. So 2 to the power of 3 times 2 to the power of 4 is 128. Well, let's check 2 to the power of 7. In fact, I'm going to write that down first. 2 to the power of 3 times 2 to the power of 4. This was 128, just so that I have that kind of recorded. Now let's see what 2 to the power of 7 is. 2 to the power of 7, or you could just write 2 times 2 times 2. Also, on my calculator, which you can't really see, it's also 128. Does 128 equal 128? Yeah, it does, which means these are equivalent. 2 to the 3rd power times 2 to the 4th power is essentially 2 to the 7th power. That's called product of powers. This step right here is called simplifying. Simplifying means, in this case, to write your expressions as a single power. So we call this a single power. Single usually meaning alone, or single meaning one. So we had 2 powers here. Now we've written it as a single power over there. And this step is called simplifying. And that's how product of powers works. So let's try another example. This time, instead of our numbers, let's do one more with numbers. How about that? What if I have 4 to the 2nd power times 4 to the 3rd power times 4? Ooh, so I have 3 different powers now. Again, if you can't see that, that's 4 to the 2nd power times 4 to the 3rd power times 4. Let's write that as a single power, and then we'll use our calculators to check our work. So we start off the long way, just the same way that we did before. We're going to expand them as powers, as products, excuse me. 4 to the 2nd power is 4 times 4, okay? 4 to the 3rd power is 4 times 4 times 4. And 4 is just 4, which, by the way, you can write 4 as a power. If you have a single digit, that just means 4, kind of like the hidden 1 power. So we have 4 times 4 times 4 times 4 times 4, right, you get the idea. Okay, so we have 4 right here. All right, and then what are we really doing? We're multiplying these by each other. So we have 4 times 4 times 4 times 4 times 4 times 4, right? We're just continuing that multiplication. So just like we did in our first example, can I write this as a single power? Well, you're just going to basically see how many times you're multiplying 4 by itself. So I have 4 times 4, so that's 2 times, and then 3 more makes 5, and then that last one makes 6. So 1, 2, 3, 4, 5, 6. So I can write this as 4 to the 6th power. Now, if you don't believe me, grab your calculators and let's see if these are actually equivalent. So using my calculator, this time I'll do it the long way. 4 times 4 is 16, times 4 times 4 times 4 times 4. And I got a pretty large number here. I got 4,096. I'm just going to double check that. 4 squared times 4 cubed times 4. Yep. So when I multiplied all of this out using a calculator, I got 4,096. Big old number, right? Let's see if when I do 4 to the 6th power, it gives me the same answer. 4 to the power of 6, look at that, also 4,096. Are these equal? Yes, they are, which means this power is equivalent to that product. The only difference is this is a product of powers. I'm multiplying powers, and this is what we call a single power. One power standing on its own. Okay, last example. Let's take out the numbers and let's look at an example with variables. We did X's over here, so let's choose a different example. It is May the 4th, so let's use M. So let's say I have M to the 5th times M to the 2nd times M to the 3rd. All right, so M to the 5th times M to the, I didn't do M to the 4th. I should have, but I didn't. Oh well, what are you gonna do? Times M to the 2nd times M to the 3rd. So we start off with our normal routine. we're going to expand them. So that's m to the 5th. M times m times m times m times m. 1, 2, 3, 4, 5. 5 m's. M to the 2nd is m times m. Oh my gosh, I'm running out of room. This is really tedious. I don't know if you've noticed that or not, but like, wouldn't it be great if we just had a shortcut? Well, I just have to write out all these m's. We will have a shortcut. All right, stick with me. And then m to the 3rd is m times m times m. Oh gosh, my hand is hurting, right? From writing all of that out. Miss Angel, do we have to write this out every time? No, because there is a pattern that will arise here. Okay, how many total m's? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for a grand total of m to the 10th power. Oh, awesome. Now we can't check it using a calculator because like you can't plug in m to the 10th power on a calculator, but you can basically use your expansion here to check for you. Now, again, that was a lot of work. Like, wouldn't it be great if there was just a pattern that was arriving every single time that we wouldn't have to write it out every single time? Well, let's see if there's a pattern between our products of powers and our, again, we call these single powers. Okay, we had 2 to the 3rd times 2 to the 4th equal 2 to the 7th. Wonder if there's a pattern there. We have 4 squared times 4 to the 3rd times 4 was 4 to the 6th. Then we had m to the 5th times m squared times m third. Is there a pattern that you notice that we could actually, without having to expand, we could jump straight from here to there? Really, what I notice is that when you're counting up the total 2s or counting up the total 4s or counting up the total m's, you're actually adding, aren't you? Like there's 3 here plus 4 more for a total of 7. There's 2 here plus 3 more plus 1 more for a total of 6. There's 5 plus 2 more plus 3 more for a total of 10. Does that work? Well, let's see. 2 to the 3rd times 2 to the 4th. What's 3 plus 4? 7. Let's see if that made sense elsewhere. 4 to the squared times 4 to the 3rd times 4 to the 1st. 2 plus 3 plus that hidden 1. 2 plus 3 is 5 plus 1 is 6. What about here? 5 plus 2 is 7 plus 3 is 10. Oh my gosh, I think we just found a pattern or a shortcut, really. When you are multiplying powers, as long as they're the same base, because if this had 3, like I couldn't continue that multiplication. We'll look at an example like that. You're really just adding up the total number of bases. I have 3 2s here plus 4 2s here for a grand total of 7 2s. I have 2 4s here plus 3 more 4s plus 1 more 4 for a grand total of 6. I have 5 m's plus 2 more plus 3 more for a grand total of 10. So that means we actually have a shortcut here. Here's our shortcut, or what in math we call a rule. Because once it's been proven, you can actually use it. So we call it a rule, or in this case, we call it a property. This is called a property of exponents. The property is called product of powers. Here's the shortcut that you can use. When you have 2 or more powers brought to different or the same exponents. So let's say I have x to the a power times x to the b power, and a and b are numbers. This could be 5 and 7, it could be 2 and 3, it could be 27 and 54. It doesn't matter what those numbers are. The rule or the property says to simplify and write it as a single power, you just add the exponents. That's it. That's all that is, right? All we did was we added 5, 2, and 3 and got 10. We added 2, 3, and 1 and got 6. We added 3 and 4 and got 7. This is called the product of powers. We're going to do a couple examples in just a second, but I want you to kind of understand how that works. You can always expand it. So if you want to go the long way, you can write it out, but it's going to take a really long time. So this is kind of like a shortcut or something we call a property. And actually at the end of the video, when we do our exit ticket, we'll look at some examples that have product of powers. Now, that was one of the properties. I know, take a quick break if you need it. We've got two more properties to go. We have quotient of powers and we have power of powers. And we're gonna look at it kind of the same way. We're gonna look for, we're gonna do it the long way first, and then we're gonna look for a pattern. So grab another piece of paper, take a quick break. We're about to go over quotient of powers. Okay, property number 2, quotient of powers. Here's how quotient of powers works, or what it actually means. What is a quotient? A quotient means division. So that basically means I'm dividing powers. Just like over here, product meant multiply. I was multiplying powers. Now we're going to look at examples where I am dividing powers. So just like we did over there with product of powers, we're going to go through this the long way. And then after doing 3 examples, we're going to see is there a shortcut? Like, is there a way that we could just go like, click, here we go. You know, let's make this easier on ourselves, right? So here we go. Let's start with number examples again, because those are easier to check because we can use calculators. So we use 2 over here. Let's use 2 over here again. So this time we're looking at a quotient of powers. So let's say I have 2 to the 5th power. Make that a little bit darker. 2 to the 5th power divided by, now remember, we don't use the little division symbol here. You're going to use a fraction bar, which fraction bars mean divided by. Divided by 2 to the 3rd power. 2 to the 5th divided by 2 to the 3rd. Now, we're going to do this a long way. So we're going to write it out, and then we're going to simplify it and write it as a single power. So just like we did with our products of powers, let's start by just expanding. Like, what does 2 to the 5th power actually mean? Let's write it out. Maybe we'll notice something, right? 2 to the 5th power means 2 times 2 times 2 times 2 times 2, right? We all know that because we saw the intro video, we talked about that. 2 to the 3rd power means 2 times 2 times 2. How the heck are we supposed to simplify this though, right? Like, that's the hard part. It's like, what do you see? That's a big part of math. Like, what do you see? What stands out? Well, there's something actually that I noticed. Both of these have 3 2's in common. So this has 2 to the 3rd power in common, and this has 2 to the 3rd power in common. And you're dividing. What would 2 divided by 2 equal? Oh, wait a minute. We learned about this in our last class. Those are called big ones. Yes, they're called big ones. And give yourself a pat on the back if you saw that from the get-go, because you are correct. These are what we call big ones. Because what's 2 divided by 2? 2 divided by 2 is 1. 2 divided by 2 is 1. Or in other words, what would 3 2's divided by 3 2's equal? 1. Yeah, this is a big one. A big one, a big one, a big one. And that leaves us with 2 times 2 in the numerator and only 1's in the denominator. So if we're writing this as a single power, now we're not simplifying, we're not saying the answer is 4, our answers are single powers. We're basically left with 2 squared over 1, which is just 2 squared. I'll go over that a little bit darker. So we had 2 2's left in the numerator, and we had just 1's, big 1's left in the denominator. So we could just write that as 2 squared. Now we use 2 for a reason. The reason why we use 2 is because we can check using our handy dandy calculators. So on my calculator, I'm just going to do 2 to the 5th divided by 2 to the 3rd. So 2 to the power of 5, which is 32, divided by 2 to the power of 3. And my answer was 4. So I'm going to write that down somewhere. So my answer here was 4. Okay. Then we did our long way, 2 squared. Now, I really hope you don't need a calculator for this. What is 2 squared? 2 squared is 2 times 2. 2 times 2 is 4. So are these equivalent? Yes, they are. They both have a value of 4. Interesting. But again, like, that's a lot of work. So start thinking about patterns that you might see here, patterns that arise, because yeah, we're going to be looking for some patterns there. All right, let's try another example. How about using 4 again? How about 4 to the power, oops, there's my paper here. 4, there we go. To the power of 3 divided by 4 to the power of 6. This one's going to be interesting. 4 to the power of 3 divided by 4 to the power of 6. Let's write this one out. So same thing, we're going to expand it first and look for, I don't know, maybe some big ones. We'll see. All right, 4 to the power of 3, what does that mean? 4 to the power of 3 means 4 times 4 times 4. Cool. 4 to the power of 6, what does that mean? That means 4 times 4 times 4 times 4 times 4 times 4. Oh, I can't wait till we figure out what the pattern is so I don't have to write out all these 4s, right? Okay, what do you see? A lot of math is just like, what do you see? Well, I see 3 4s up here, and I also see 3 4s down here. Do you notice that? There's 1, 2, 3 4s in the denominator and 3 4s in the numerator, kind of like a GCF, like what they have in common, which means just like up here, I know that those equal big ones. Like I could either make individual big ones, or I could just say, you know what? That equals 1. Like 4 times 4 times 4 divided by 4 times 4 times 4, that's just 1. Or I could go in like I did here and make individual big ones. But those, for lack of a better term, cancel. I hate that word, but they do. Essentially, they're canceling. They equal 1, so they're no longer parts of our product. So what does that now leave us with? Well, we have to look at this still as a fraction. What are we left with in the numerator? Well, all of these became 1. So that leaves us with 1 in the numerator. And then what's left in the denominator? 4 times 4 times 4, which we would write as 4 to the 3rd power, right? And then can I simplify that any further like I did here? Well, no, you can only simplify when 1 is in the denominator. So this is just our final answer, 1 over 4 to the 3rd power. That's our single power. And that's our final answer. We've done the simplifying. We've done as much as we can. Make that a little bit darker. Now, same thing. Let's grab our calculators and let's see if that's actually true. So in our calculators, we're going to go 4 to the 3rd power, which is 64, divided by 4 to the 6th power. Ooh, I got a really interesting decimal here. Let's see. My decimal was 0.015625, right? Let's see if I get the same thing when I just do 1 divided by 4 to the 3rd power. I get 0.015625. Are those equal? Yes, which means these are equivalent. Yeah, they're equivalent, right? Kind of interesting. Okay, let's look at one final example, and then that will allow us to hopefully make a rule. Because then once we do a rule and a property, we don't have to do all this long work of like writing things out. Let's use m's again. All right, so let's say I'm going to make this one fun. Yay! I looked a little creepy there. Let's say I have m to the 5th times m to the 2nd divided by m to the 6th. Ooh, what? Did I throw in a power? Yes, I did. Okay, I know, I got really excited. You know me, I love doing stuff like this. All right, so we'll expand it and then we'll look at a final answer. So m to the 5th power times m to the 2nd power. Let's use what we learned over here. What can I do with the exponents when I'm multiplying powers? Oh, I can add them. So really m to the 5th times m to the 2nd is m to the 7th, which means there are 7 total m's. 1, 2, 3, 4, 5, 6, 7. Look, I just applied a property while learning about another property. Crazy, right? So I've got 7 m's in the numerator, and I've got 6 m's in the denominator. 1, 2, 3, 4, 5, 6. What do they have in common? Well, we've got 7 in the numerator, 6 in the denominator, which leads me to understand that they're going to have 6 in common. So I can pull these 6 and pull these 6. And what would 6 m's, or m to the 6 divided by m to the 6 equal? That would just equal 1. So I can make all of these 1s, or I could make them all one big one. And then the final question is, what do we have left? Well, in the numerator, we have an m. And in the denominator, we just have a bunch of 1s, which means we just have 1 left over. And what's m divided by 1? Well, m divided by 1 is just m. Now remember, and we can't really check with that one because it's variables and you can't multiply variables, but we would leave our answers like this because these are all called, do you remember what they're called? I'll give you a hint. Same thing over here. These are all called single powers. Write your answer as a single power, 1 power. Don't simplify it, just write it as a single power. All right, now, can you do this every single time? Can you write it out? Totally, go for it. If you want to write it out every single time, by all means, go to town. But that's a lot of work. Like, the more complicated these problems become, you don't want to write it out every single time. So in that case, do we see a pattern, which then we could write a property, so a shortcut that we can use from now on? Well, we had 2 to the 5th divided by 2 to the 3rd, and we ended up with 2 squared. 5 in the top, 3 in the bottom, ended up with 2. Then here we had 4 to the 3rd divided by 4 to the 6th, and we ended up with 4 to the 3rd, but in the denominator. Here we had m to the 5th times m to the 2nd, which we knew was m to the 7th. I'm going to write that in here. So we knew that this was m to the 7th divided by m to the 6th, and we left with just m, just a single m. What could be the pattern? Wait a minute. How do you get 2 from 5 and 3? 5 minus 3 is 2, isn't it? Yeah, 5 minus 3 is 2. I believe that. So here, I could subtract the exponents. 5 minus 3 is 2 and get 2 to the 2nd power. What about here? I'm going to skip this one for a second. What about here? I have 7 up here. 7 minus 6 leaves me with 1, which m is just m to the 1st power. Yeah, 7m over 6m leaves me with 1m. 7 minus 6 is 1. What about here? I had 3 4s and 6 4s. Well, hold on. 3 minus 6 is negative 3. What the heck does that mean? We're going to actually talk about negative exponents a little bit later on. But for now, let's look at it as which one had more? The denominator has more. So let's actually work backwards. What's 6 minus 3? Well, 6 minus 3 is 3. So that means I have 3 left over in the denominator. And that actually has something to do with the exponent being negative 3. So really, I looked at which one had more, and then after subtracting them, my answer had that as an exponent. 5 minus 3 is 2 to the 2nd power in the numerator, because the numerator had more. 6 minus 3 is 4 to the 3rd power in the denominator, because the denominator has more. By more, I mean more factors. And m to the 7th divided by m to the 6th, 7 minus 6 is 1 in the numerator, because the numerator had more. So that means when I have a quotient, like let's say x to the a power divided by x to the b power, how can I simplify it in one step? I'm going to subtract A minus B. Now, and again, you might end up with a negative right now, and that's totally okay. We will deal with that later. Just remember, A is always the greater number. So in this case, we subtract 6 minus 3, but we keep in mind that the denominator has more factors of 4, which means that my final answer is in the denominator. That's called the quotient of powers property, and that's a quicker way to simplify these types of problems. All right, we have got one more property to learn today. And I know it's like, oh my gosh, there's so much to learn, but you'll be okay. Trust me, this is the longest we will ever spend on these properties. Once you understand these shortcuts, it's going to be so quick. The last property we're going to learn today is called power of powers. So get your pencils and papers ready, or take a break if you need to. Here we go. Okay, we're almost there. You're doing such a great job. Here's our last property for today, power of powers. So just like a product of powers means multiply powers, I'm trying to point, and quotient of powers means divide powers, power of powers means we're going to take a power and we're going to raise it to another power. It's crazy. It's like a power within another power, like an onion having a lot of layers. Maybe not, I don't know, that didn't sound right. But anyways, you get the idea. So again, the property will tell you what you're looking at. We're looking at products, we're looking at quotients, we're looking at powers. Here we go. So for our first example, we'll keep with the pattern here. We did 2s, we did 4s, and we did m's. Again, we will look at it long ways, and then we'll look for patterns. So for this one, let's say I have 2 to the power of 2. We'll keep it simple to start. 2 squared raised to the additional power of 3. What? Basically, a power raised with another power. So this is a power raised to a second power. Just like this was a product of powers, a quotient of powers, we have a power raised to another power. I know, your mind's going nuts though, right? So first we'll look at the long way, like what does this mean? And then we'll write it out as a single power and see if we can find a pattern, because patterns, we like patterns. Patterns mean that we don't have to do all that work. Now, I want you to remember here, powers mean repeated multiplication. This is called the base of the power. Just like over here, 2 to the third power was 2 times 2 times 2. Well, 2 squared to the third power is the same idea. It's just 2 squared times 2 squared times 2 squared. It's just, oh, that's a 3. Ah, sugar. Well, you know what I mean. That's a 2 squared. Pretend like that was a 2 all along. I was about to say 3 and then I got ahead of myself. So basically 2 squared to the third power just means 2 squared times 2 squared times 2 squared. Just like 2 to the third power is 2 times 2 times 2. This is the base, and you're multiplying this by itself 3 times. Well, how do we write that as a single power? Well, remember, what we've really done here is we've taken a power and we've written it as a product, which means we can use this property to simplify it. I have 2 squared times 2 squared times 2 squared. Remember, when you have a product of powers and they all have the same base, what can I do with these exponents? I can add them up. I've got 2 here, plus 2 more here, plus 2 more here, for a grand total of 2, 4, 6, 2 to the power of 6. Right? So I've got 1, 2, 3, 4, 5, 6. 6 total 2s. And remember, this is called a single power. Single power meaning just one. Now, there's a reason why we chose numbers first. Let's go ahead and see if that's actually correct. So we're going to take 2 to the power of 2, 2 squared, and then we're going to raise that to the power of 3. So 2 squared is 4 to the power of 3. I got 64. So over here, my answer was 64. Okay, let's see if I get the same answer when I just do 2 to the power of 6. 2 to the power of 6. 64. Does 64 equal 64? Yes, they do, which means these are equivalent expressions. Look at that. So a power of a power, you do the same thing that you would normally do with any old power. It's just you're going to write it out as multiplication, and whatever's inside the parentheses, whatever the base is, that's what you're multiplying by itself. All right, let's try another one. How about using fours? Let's try 4 to the 5th power, so 4 to the power of 5, raised to the power of 2. I'll be nice. Raised to the power of 2. So this is our second example. 4 to the power of 5 raised to the additional power of 2. So this is why we call it a power of powers, because it's a power raised to an additional power. Okay, just like we've been doing, let's go ahead and write it out, expanded form. So 4 to the power of 5 to the power of 2. This is your base. So I'm basically multiplying 4 to the power of 5 by itself 2 times. So that's 4 to the power of 5 times 4 to the power of 5. And then from there, we can use our product of powers again, because I've taken my power and I've written it as a product. So let's see, I've got 5 fours over here, 1, 2, 3, 4, 5, plus another 5 over there. 5 plus 5 is 10. So 4 to the power of 5 to the power of 2 is 4 to the 10th power. And again, remember, that's called writing this as a single power. Okay, cool. Now, let's grab our calculators and let's see if that's actually true. So I'm going to do 4 to the power of 5, which is 1024, raised to the power of 2. That is a big number. I got 1,048,576. Huge number, right? Let's see if 4 to the 10th power gives us the same thing. 4 to the power of 10 is 1,048,576. Are those the same? Yes, they are, which means these are equivalent. All right, keeping with what we were doing before, let's try one this time with variables. So let's say I have, should I? Yeah, I'm going to. I just had an inner monologue in my head. What if I have m to the 3rd power times m to the 4th power raised to the 3rd power? What? I know, she's going crazy. What does that equal? Well, for this one, I basically just blended. So remember, m to the 3rd times n to the 4th, I can write that as a single power. I've got 3 m's here and then 4 more m's there. So before you do anything else, I would write this as a single power. So what's m to the 3rd times m to the 4th? I've got 1, 2, 3, 4, 5, 6, 7. The first thing I would actually do here is write that as m to the 7th to the 3rd, right? Just like deal with what you can first, because it'll make your life a little bit easier as you go along. All right, so now that I've written this as a single power, let's raise m to the 7th to the 3rd power, meaning this is my base. I'm going to multiply m to the 7th 3 times. How do I know 3 times? Because that's my exponent, times m to the 7th times m to the 7th. So I've got 3m to the 7th. That's a lot of m's. I've got 7 m's here, 7 more m's here, and 7 more m's here. 7 plus 7 is 14, plus 7 is 21. Crazy, right? So that also equals m to the 21st power. Now we can't check that using a calculator because we were using n, but that's okay. We call this a single power. All right. Now this one doesn't require as much work as product and quotient does, but still, wouldn't it be nice if we could just notice a pattern here and then we could just use the pattern? Like that would be so nice, right? So let's see if, just like the other ones, is there a pattern that we notice here? Let's look at our first example. We had 2 to the power of 2 raised to the power of 3, which means I had 3 sets of 2 or 3 groups of 2. 1, 2, 3, each of them raised to the power of 2, and I got 6. 3 groups of 2, 6. Here I had 4 to the 5th raised to the power of 2, which basically means I have 2 groups of 5, 5 and 5, and I got 10. And then here I had 3 groups of 3 and 4, which I combined these, right? And end of the 3rd times end of the 4th times end of the 7th. So basically I had 3 groups of 7. 1, 2, 3 groups of 7. Could there have been a quicker way? Well, groups of, isn't that repeated addition really? Like 2 plus 2 plus 2 is 6. So I'm adding 2 3 times. Does 3 times 2 equal 6? Yeah, it does. Here I'm adding 5 2 times. Well, repeated addition, like we did in our last video, 2 times 5 is 10. 3 times 2 is 6. 2 times 5 is 10. What about down here? Well, after we combine this, 3 times 7 is 21. Would that have worked here? 3 times 3 is 9. 3 times 4 is 12. What's 9 plus 12? Also 21. Oh, so interesting. What we're doing here is we're actually, because we end up adding these up, the number of times that the exponent is, you're really multiplying. Like I multiply the 2 powers and it gives me my final answer. So that means when you have a power, like let's say x to the a power, and again, a could be any number, raised to an additional power, the quote shortcut here, the pattern, is that you just multiply them together. Because you're going to end up adding up this exponent this many times. I added 7 3 times. I added 5 2 times. I added 2 3 times. And as we saw in our last video, repeated addition is just multiplication. I know, totally crazy, right? So what we're going to do is we're going to wrap up this very intense and long video looking at some examples, just some very basic examples where we would apply one of these 3 properties, either product of powers, quotient of powers, or power of powers. We're going to wrap those up, and then you're going to have a little bit of additional practice to do kind of on your own. So bear with me. We've only got a few more minutes left to go. Okay, welcome to our exit ticket. So what I've done is on the top of my whiteboard, I have written out the 3 rules or the 3 patterns that we noticed. In a product of powers, meaning when you multiply 2 powers together, you're just adding on more factors, which is why you can add the exponents. In a quotient of powers, you end up canceling, which I don't like that word, but you get the idea. You end up creating big ones. So whatever number is larger, that number you're going to subtract the smaller one, and you'll be left with that number or that power as your single power. And this one is a little bit complicated because we haven't talked about negative exponents yet, but we will get there. And then power of powers means that I'm just taking this many groups, whatever the outside power is, of the inside. So I just multiply the exponents together. These are the properties. They are the shortcuts. You don't have to use them, but if you don't want to write out your work every single time, I highly suggest you start to at least get used to them. Okay, so we're going to look at a few examples here. In fact, we're going to do 5 total examples. I'm going to write them up just one at a time. We're going to talk about which one they represent. So like what rule are we looking at here? And then we're going to use the rule, get our answer in really like less than 10 seconds. I mean, once you are able to understand how these properties work, the work is super fast. So let's look at exit ticket number 1. Okay, and again, this is our exit ticket. If you want to write this down on your piece of paper, I highly suggest that you follow along. Okay, so again, our goal here is to write these as single powers. That means don't actually simplify, just write it as its own single power. So let's start off with n to the 3rd power divided by n to the 5th power. Okay, that's our exit ticket number 1. Feel free to pause if you want to try it on your own. The first thing we're going to do here, if you've paused and unpaused, is identify which of the 3 properties is it. Well, it's division. Division means quotient. So because I'm dividing 2 powers, that means this is a quotient of powers. So I know that this follows this rule. Now I could then go the long way and write it out. N times n in the numerator, n times n times n times n times n, whatever, 5 n's in the denominator. But let's use the rule. Let's just do this quickly, right? Like, let's actually do something fast for once in our lives, right? When it comes to math. So quotient of powers, you take the larger exponent and you subtract the smaller one, because right now we have not talked about negatives. We've got 3 n's in the numerator, 5 n's in the denominator. What is 5 minus 3? 5 minus 3 is 2. But where are those n's? Are those 2 remaining n's in the denominator or the numerator? There's more down here, which means that my final answer is going to be 2 n's in the denominator. So essentially, the math that I'm thinking about, this is what I'm doing in my head. I'm doing n to the 5 minus 3. That's what I'm doing. I'm subtracting 5 and 3, and I'm getting n to the second power. But this isn't my answer, because again, where are more of the n's? More of the n's are in the denominator. So my answer is, I'm left with 1 in the numerator, because when I had all those big ones, I'm left with just 1, and I'm left with 2 n's in the denominator. Because 5 minus 3 is 2, but I'm left with more in the denominator. Look at that. Aside from the fact that I had to explain it a lot, the actual math of it took 10 seconds, less than that, right? So quotient of powers, more n's in the denominator. I'm left with 2 n's in the denominator, no n's in the numerator, which means I'm just left with n's. And that's called a single power. Okay, exit ticket number 2. How about this one? How about 5 to the power of 4 raised to the power of 3? Okay, now what's nice about these ones is that because I gave you a base that's a number, you can always check your work by grabbing a calculator and figuring out what this number is. So in a calculator, I would go 5 to the power of 4, which is 5 times 5 times 5 times 5, which I think is 625 if I have that off the top of my head, and then raise it to the power of 3. You're going to get a pretty large number, but then you can check your final answer at the end and see if it's equivalent. Now, which of these 3 properties can I use? Am I multiplying 2 powers here? No. Am I dividing powers here? No. Am I taking a power of a power here? Yes. So this is an example of power of powers. That means I'm taking 5 to the 4th power and I'm multiplying it by itself 3 times. So remember, if you're going to expand it, it would be 5 to the 4th times 5 to the 4th times 5 to the 4th. But we're going to use the shortcut. The shortcut is, this basically means I have 3 groups of 4 5s. 3 groups of 4. So the math that I'm doing in my head, this is what's happening in my head, is I'm doing 5 to the 4th power 3 times. I'm multiplying these because I have 5 to the 4th times 5 to the 4th times 5 to the 4th. That's 3 groups of 4. So my final answer is I have a grand total of 5 to the 12th. 5 to the 12th. 12 total 5. 3 groups of 4 is 5 or 12 total 5, or 5 to the 12th power, and that's it. You are done. That's called a single power. Check it using a calculator to see if I'm right, and let's go ahead and set up number 3. Number 3, here we go. Let's say I have 4 to the 7th power times 4 times 4 to the 3rd power, okay? So now I've got 3 factors here. So which of these properties am I going to use? Is this a product of powers, a quotient of powers, or a power of powers? Well, I'm multiplying powers. Multiplication means product. So this is a product of powers. So I'm going to use this property, product of powers, okay? Now, I could write this all out. I could write out 7 4s and then another 4 and then 3 more 4s and add them all up. I could totally do that. Well, it seems like a lot of work. Like, wouldn't it be great if I could just do this quicker? So remember, with product of powers, the rule or the property says all I have to do is add the exponents, because you're essentially adding more factors. So let's figure out the math that I'm doing in my head. So in my head, what I'm really doing is I'm taking 4 and I'm adding the 3x with 3. Wait, hold on. There should be 3 exponents here. There's only 2. What's the hidden exponent of the 4? Hidden should have told you what the answer is. There's always a hidden 1 here. So even though it won't be there right away, in fact, I'm going to do it in a different color to show that, you can always put in like a placeholder 1. There's 1 factor of 4 there. That needs to be considered. Okay, so in my head, the math that I'm doing is I'm just going to add them all up. I've got 7 4s plus 1 more 4 in the middle plus the 3 on the end. So I've got 7, 8, 9, 10, 11. My grand total is 4 to the 11th power. And that's our single power. And again, because it has a base that's an actual number, you could totally grab a calculator and check this. 4 to the 7th times 4 times 4 to the 3rd, and then check 4 to the 11th and see if that's correct. Now, our last 2 examples are going to be a little bit trickier just because I want to push and see how well you can understand these properties. So get ready for 2 more exit ticket examples. Okay, exit ticket number 4. This one is trickier than it looks. I have 2 to the 4th power times 3 to the 2nd power times 2 to the 5th power. Now remember, my goal here is not to figure out the answer. Like I don't need to know what like the large actual number that this equals. That is not the goal here. The goal is to write this as a single power. So like 1 power raised to an exponent. For this one, I'm actually going to write it out just because there's something tricky here. If you notice, I have 2 to the 4th power, but then I have 3 to the 2nd power. So like, what can we do there? Let's see. So for this one, I'm actually going to write it out just to show my point. 2 to the 4th power is 2 times 2 times 2 times 2, right? And 3 to the 2nd power, I'm going to use a totally different color because like, what the heck is that 3 coming from? Use green. 3 to the 2nd power is 3 times 3, and then 2 to the 5th power is 2 times 2 times 2 times 2 times 2, right? And then what am I doing? I'm multiplying these together. Now, here's the thing with repeated multiplication. I notice that I have repeated 2s. Like I've got more 2s over here, but can I say that like 2 times 3 is 2 to the 2nd power? Or like 2 times 3 is 3 to the 2nd power? Like, doesn't it look like those 3s don't really belong? They can be part of my answer, but I can't use them in product of powers. So this is a product of powers, but you have to be careful here. You can only simplify powers that have the same base. So I can write these 2 as a single power, but that 3 to the 2nd power just kind of has to come along for the ride. Like there's nothing I can do with it. I can't add it into my power. So if I have 4 2s here and 5 2s here, that's a grand total of 4 plus 5 is 9. So that would be 2 to the 9th power. But then what do I do with the 2 3s? You just write them as part of a product. That's just times 3 to the 2nd power. That's it. That's all that you can do. This is technically, even though it's not a single power, both of these are simplified, or you've done as much work as you can do. So if I were to do this in one step, I would notice that I have the same base 2, so I could add these exponents. 4 plus 5 is 9. And then what could I do with this 3? Just bring it along. And then again, because it's an actual, it actually has numbers in it, you can check using a calculator, but this is your final answer. This is all that you can do here. So it is a product of powers, but you can only simplify it. You can only apply this rule if the powers have the same base. One last problem, and for this one, we're actually going to go even a little bit trickier than that. Okay, bear with me. This one looks a little crazy, but it's actually really not that crazy at all once you think about what you're looking at here. So this is by the way, this is kind of where we're heading. We're heading toward problems that look like this, where you're going to have to blend different properties together. So for the sake of today, we're going to keep it simple, but just understand that you're going to have to do some stuff that kind of looks like this. So we have x to the 3rd times y to the 2nd times x to the 5th, all divided by x squared times y to the 3rd. So this is what we call a combination of properties. It's clearly a quotient. I mean, hopefully you can see that it's a quotient because it has a big old fraction bar. But in the numerator, we're also dealing with product of powers because we have the x cubed and the x to the 5th. So my recommendation this is how I think about it. I'm going to apply the property in the numerator and denominator separately first, then I'm going to do the quotient. So let me show you what I mean. I'm going to use the properties here. First thing I'm going to do is I'm going to notice, okay, I have x to the third here and x to the fifth here, and I have that little y squared in between, but I'm not worried about that. What if I just go ahead and I write these as a single power? So if I have 3 x's times 5 more x's, 3 plus 5 is 8. I can write that as x to the 8th power. You see that? 1, 2, 3, 4, 5, 6, 7, 8. And then the y squared comes along for the ride. And then I can't really do anything in the denominator just yet because those are 2 different bases. Now, am I done here? Definitely not. All I've done is I've applied the product of powers. Yay. But I still have to apply the quotient of powers. So to do this, again, I'm going to use these shortcuts, the properties. The properties state in a quotient of powers, take the larger exponent and subtract the smaller exponent. So from here, it would be 8 minus 2. And here, it would be 3 minus 2. Notice I'm only doing that with the same variable. Like I can't make a big 1 with an x and a y, but I can make big ones out of x's and x's. So I'm going to do this in one step, just so that you see. And again, you won't have to do problems like this just yet, but this is what's coming. I'm going to do this in one step just so you see how simple this can be. Ready? 8x's in the numerator, 2x's in the denominator, which means I'm taking away these 2. What is 8 minus 2? That would be 6. But am I left with 6 in the numerator, or am I left with 6 in the denominator? Well, which one has more? 8 is clearly more. That means I'm left with x to the 6th in the numerator. 2 of these x's became big ones with these 2 x's. So that leaves me with x to the 6th in the numerator. Okay? I've got 2 y's in the numerator, but 3 y's in the denominator. Which one has more? The denominator. So what is 3 minus 2? That leaves me with 1 y. But where is that y? Is it up here? No. Both of these y's are gone, and I'm left with y to the first power in the denominator. Or I could just write that as x to the 6th divided by y. So I'm going to show you another way to kind of think about this. I'm essentially taking these 2 x's and taking them out of these 8. So these are now gone, and I've taken 2 away, which leaves me with 6. That's kind of what I'm doing, all right? And then the same thing with the y's. I'm taking these 2 y's and subtracting them from these 3. So these are gone, and that leaves me with 1 left over. So as you can see, I'm left with x to the 6th in the numerator, y to the 1st in the denominator, and y to the 1st is just y. All right, that is it. You've made it to the end. I know this video is like ridiculously long, but this is the only time we'll go into these properties in such great detail. So I won't say have fun factoring anymore. Now it's have fun applying properties. That doesn't sound as cool. I'll figure out something. Anyways, have a great Star Wars Day. May the 4th be with you.